In this video I'll be looking at ionization energy, and hopefully you'll see that after discussing ionization energy it will help us to advance our model of the atom that we looked at in previous videos. So what is ionization energy? It's essentially the energy needed to remove an electron to form positive ions from a species. A beam of electrons from an electron gun is used to remove an electron from a species to form a positive ion. The amount of energy required to remove the electron is recorded. So the first formal definition we'll look at is called the first ionization energy, and it's quite an important one. So I've got it up here. The first ionization energy of an atom, of an element, is the minimum energy that's required to remove the most loosely bound electron from a gaseous atom in its ground state. And we can represent that by an equation. So for sodium, for example, it would be the sodium atom with G for a gaseous state, that's its state symbol, going to the sodium ion, also G for gaseous, plus an electron. And that is the equation for the first ionization energy of sodium. Technically, the definition should read that it's the energy required to remove 1 mole of the most loosely held electrons from 1 mole of gaseous atoms to produce 1 mole of gaseous ions. But the definition above will definitely work for the leaving cert chemistry, and it's easier to deal with. But what we want to do then is we want to use this theory to build up and develop our model of the atom. And to do that, we're going to look at successive energies. So not just the first ionization energy, we're going to look at the second ionization energy. That's to remove 1 mole of electrons to form 1 mole of gaseous 2+ ions from the 1+ ions. We're going to look at the third ionization energy, which is to remove 1 mole of gaseous electrons from the 2+ ions to form 3+ ions, etc., etc. And what we're going to find is when we look at a series of figures for successive ionization energies for an element, we're going to find that some of the numbers are going to be relatively similar, i.e. there's not that much difference in taking a successive electron, and then we're going to find a massive jump in ionization energy. Now the reason for that jump is probably because that next electron is removed from something that's closer to the nucleus. So the next thing we'll do is we'll look at sodium's successive ionization energies. Now I've drawn out a list here, but I haven't included all of them. So with this list we can see that the first ionization energy, and it's worth noting that this is in kilojoules per mole, is 496, which is relatively small. So it's quite easy to remove sodium's first electron. And it gets successively higher. That's what happens with ionization energies. They get larger and larger as you go and try and take away the next electron. To understand this in a bit more detail, we're going to have a quick look at the electron shell structure for sodium. We know that the first electron to be removed is this electron here. It's on the outer shell, and that has an energy of 496 kilojoules per mole. So the next electron to be moved will be from a shell that's closer to the nucleus. Okay, so this shell here, this green shell, is closer to the nucleus, and so we can see that the second ionization energy is going to be a lot higher than the first, because it's a lot harder to take away this electron from this shell compared to the outer shell here, where this electron was much further from the nucleus. So I haven't included all of these ionization energies here, but they go up gradually, okay? The next big jump we notice is on going from the second energy level to the first energy level. The 10th electron to be removed here has a much larger ionization energy than the 9th. So again, this is further evidence to the idea that electrons not only get further away from the nucleus, but are housed in energy levels which are a certain distance from the nucleus, and those energy levels themselves can house a certain number of electrons, and in this case the second energy level hold 8 electrons. So now let's look at the theory of why these electrons, or how they are attracted to the nucleus. So if I draw a model here with the nucleus in the middle, which is a positive core, an electron orbiting around it. Okay, we want to essentially see what is it that's attracting or that's increasing the ionization energy of a certain electron. Well, the first thing we'll look at is the nucleus. Okay, so this contributing factor will be what's called nuclear charge. I'll just write that here. Okay, nuclear charge. What that means is the more protons an atom has in its nucleus, the stronger the attraction between that nucleus and the outer shell electron. Because the protons are positive, electrons are negative, they will attract. The higher the positive charge here, the greater the attraction between that electron and that nucleus. So an increasing nuclear charge will increase the attraction between that electron and this nucleus, and so increase the ionization energy. The next thing we'll look at is this, okay, the distance between the electron and the nucleus, which is called the atomic radius, or ionic radius for certain successive ionization energies. Okay, the greater the distance between that electron and that nucleus, then the lower the ionization energy, because the easier it is to remove. Okay, so for a high ionization energy you want a high nuclear charge but yet a small atomic radius. The last thing we're going to consider here is something known as electron shielding. Now what that means is that, as we know, if there's inner shells of electrons, then those electrons will actually repel the other shells of electrons. Within shells there's slight repelling, but the energy levels or shells here will repel each other. So the greater the electron shielding here, the easier it is to remove the electron, and so the lower the ionization energy. To recap, the reason atoms and ions of any element will have different ionization energies is because each will have a different nuclear attraction to the outermost electron. The reason for that is, one, nuclear charge. The greater the nuclear charge, the greater the force of attraction to the electron. The second is atomic radius. The greater the atomic radius, the smaller the nuclear attraction. That's because the distance is getting bigger. And the third is electron shielding. Inner shells repelling outer shells. So the greater number of shells, then the smaller the nuclear attraction. The last thing to note is that a higher nuclear charge is offset by both the atomic radius and electron shielding, i.e. the atomic radius and the electron shielding will have a far greater role to play. So now that we've explained this, we're going to have a quick look at the periodic table. So this is from the log tables. This is a chart of the first ionization energies of the elements. And what we're going to look at is we're going to see, well, what happens to ionization energies generally on going across the period, and what happens then on going down a group to the ionization energies. And we're going to use our criteria for understanding ionization energies to try and hopefully come up with reasons behind it. So on going across the period, what we know happens is that you get more protons. So let's look at period 2 here. Each successive element, there's extra proton in the nucleus. The atomic radius is actually getting smaller because the outer shell of electrons is getting pulled closer to the nucleus because there's an extra proton in the nucleus. So that extra proton pulls in the outer shell electrons. So we know that on going across the periodic table, the atomic radius actually gets smaller for each element. So the smallest element is actually helium, because the number of protons gets bigger and bigger, and so therefore that pulls in the extra, or the electron shell. So an increasing nuclear charge, i.e. more protons, and a smaller atomic radius with negligible difference in shielding, because the electrons are being added to the same shell, means that we do expect a general increase in ionization energies, and this is actually what we get. Okay, there are some anomalies which we're going to develop in a later video. On going down the periodic table then, what we expect is, we know that the nuclear charge is increasing because you're getting more and more protons, but what's happening to the ionization energy? Actually, it's going down. Okay, the reason for that is because the outer shell electron is actually getting further from the nucleus. Also, the electron shielding is increasing. So on going down the periodic table, ionization energies will decrease, and on going across the periodic table, ionization energies will increase. Now, there are a number of exceptions which we're going to develop in a later video. For example, I'm going from beryllium, boron, there's a decrease. I'm going from nitrogen to oxygen, there's a decrease. This tells us that all of these electrons potentially aren't on the exact same energy level, i.e. it might be subdivided, and that's going to be the next video. So just to recap, ionization energies tell us how attracted the outer shell electron is to the nucleus. The higher the attraction for that electron to the nucleus, the higher the ionization energy, i.e. the harder that electron is to remove.